Let's see. Actually, I should change microphone. Should I change it? Yeah, it's okay. That's okay. Am I live? We're gonna see. So, am I live? So, today we're gonna read this book, chapter 3. But before that, I need to go to just camera. The fuck is this? Why my camera is look like this? Okay. I don't understand it. So maybe before that I need to change Twitch settings. Yes, creator dashboard, manage stream. So yeah, chapter 3 reading. Yeah, so I think that's it. Programming. Okay. So okay, let's get back to desktop. So first, yeah, I was just reading this book. It's called Programming Massively Parallel Processors, a hands-on approach. And I'm also following CUDA mode server. I'm learning low-level programming. Actually, it's parallel programming and CUDA optimizations for machine learning and hopefully LLMs. Deep learning, actually, not LLMs. So let's. Okay, where is the table of contents? I need to see sidebar. Yeah. So I just read this introduction chapter, and then it's mostly about introduction to parallel programming, what is parallel programming, why it's useful, and then I read this chapter, heterogeneous data parallel computing. It's all about how this parallelism works and using CUDA C program structure, you are writing your own first CUDA code for vector addition kernel, your first CUDA kernel, and also data parallelism, where is data stored in your parallel processing, and also kernel functions and threading, how threading works, what is greed, and yeah, calling for kernel functions and compilation, how is compilation works, etc. And then yeah, this is like this is your first CUDA function, a simple traditional, not CUDA. So where is the CUDA code? Yeah, this is the CUDA function. So your memory allocation in CUDA for your data, and then you are copying the data from host to device, and then copying device from device to host after that, and all this kind of stuff. I think it looks like definitely fun. And also I did some exercises in here, as you can see. And yeah, so it's time to read chapter 3, and I have like 1 hour. After 1 hour there is Mary's uh, accountability event, weekly discussions, etc. And that's I'm gonna I'm gonna drop in 1 hour. So first I need to make it continuous scroll. I guess I am here, my camera is here. So let me see. I should install Twitch application in mobile. Okay. In the meantime, I'm gonna check in browser, and we're good to go. Yeah, so I need to make it like this. So since I'm here, come on. And also, I cannot see the chat. That's why I need to install this Twitch. And again, I need to go back to camera, and just give me 1 second. Come on. And also I forgot to announce in Twitter. So there is no background music because I don't like music while reading and while working deeply. I'm doing multiple things at the same time right now. Oh my god. Copy paste. So in the meantime, I'm gonna log into Twitch in my mobile. So I guess I need to volume up. Yeah, how about now? That's better, I guess. 64.99. Two viewers. Oh my god. Who's watching right now? Two viewers. Oh, cool. So let me send a test message. Yeah. So close all the windows, quitting Safari and getting back to reading mode. And yeah, so I'm not gonna be loud because since I'm reading, I'm trying to understand what is going on behind this concept. And also, I'm gonna highlight in here something like this, and you can see what the fuck. Okay, sorry. So chapter 3 is all about multidimensional grids and data. So what is grid? Grid is where your threads are in. So there should be some kind of diagrams. Oh my god, haven't I read this far? Yeah. So it looks like this. CUDA grid organization. Multidimensional example. So there is your host device, there is your host, and there is your devices. Device is GPU, CPU is the host. So there are kernels, as you can see, and these kernel functions are processing parallelly in blocks, in threads, and inside your grid there are blocks, and inside your blocks your threads are there. So I guess I have read some kind of, I don't remember how far, maybe until here, yeah, 50 54 or something like that, but that's okay, we can read again. No thanks. 10 minutes already passed. Okay, so I gotta be quick. So in chapter 2, heterogeneous data parallel computing, we learned to write a simple CUDA C++ program that launches a dimension. Oh my god, why? Okay. Yeah, that's better. So we learned to write a simple CUDA C++ program that launches a one-dimensional grid of threads by calling a kernel function to operate on elements of one-dimensional arrays. A kernel specifies the statements that are executed by each individual thread in the grid. So, as I said, there are grids, there are blocks, and each block has a lot of threads, and all your parallel computation is happening on those threads. In this chapter, we will look more generally at how threads are organized and learn how threads and blocks can be used to process multidimensional arrays. So in the chapter 1 and chapter 2, chapter 1 was just introduction. In chapter 2, it was one-dimensional CUDA program that does vector addition. And right now we are gonna look at image blur example. And since images has like 3 dimension or red, green, and blue, this is gonna be like more likely multi-dimensional array. So multiple examples will be used throughout the chapter, including converting a colored image to a grayscale image, blurring an image, and matrix multiplication. These examples also serve to familiarize the reader with reasoning about data parallelism before we proceed to discuss the GPU architecture, memory organization, and performance optimizations in the upcoming chapters. So it's going to be more likely to familiarize ourselves and our reasonings about data parallelism. So, and then in the next chapters, we're going to talk about GPU architecture, memory organization, and then performance optimizations. There are a lot. So in this book, if you solve the sidebar and the chapters, there are like 23 chapters, and in 22 there is advanced practices. So in 16, deep learning, merge, sorting, parallel histogram, reduction. These are all complex chapters. So we need to familiarize ourselves to understand what is going on those grids. So 3.1, multidimensional grid organization. In CUDA, all threads in a grid execute the same kernel function. Yeah, so in CUDA, all threads in a grid execute the same kernel function. This is important. And they rely on coordinates, that is thread indices. So all you can do is indicate threads. Not indicate thread. So these thread indices are so important for you to run your kernel function inside of the grid. So to distinguish themselves from each other and to identify the appropriate proportion of the data to process. As we saw in chapter 2, heterogeneous data parallel computing, these threads are organized into a two-level hierarchy. A grid consists of one or more blocks, okay, and each block consists of one or more threads. All threads in a block share the same block index, okay. Yeah, this is definitely important because as in here, you need to identify and distinguish threads from each other. And how you can do that is based on thread indices, grid block index, and then there is grid index. Probably we don't need to use grid index since all these happening inside one grid and all other kernels are running in another grid, but we need to block and threads. These are really important for us, which can be accessed via the block ID X built-in variable. Each thread also has a thread index, okay, which can be accessed via thread ID X. thread index variable. When a thread executes a kernel function reference to the block index and thread index variables return the coordinates of the thread. The execution configuration parameters in a kernel call statement specify the dimensions of the grid and the dimensions of each block. These dimensions are available by the grid dimension and block dimension variables. So these four are important: block index, thread index, grid dimension, and block dimension. Because we need to calculate how many dimension in grid we need, or we can change the block dimension based on other variables, like not these variables but other variables that you can give to CUDA kernel. Yeah, in general, a grid is a three-dimensional array of blocks, and each block is a 3D array of threads. Okay, when calling a kernel, the program needs to specify the size of the grid and the blocks in each dimension. These are specified by using the execution configuration parameters within this smaller and bigger notation of the kernel call statement. These are coming from C++ to understand it. So that's why we are calling it like CUDA C++, but it's actually not C++, it's C. You're writing all your code in C, and at the end there is just this one. It's a C++ notation. Okay, the first execution configuration parameter specifies the dimensions of the grid in number of blocks. This is dimension of grid. You can specify in here. And then the second specifies the dimensions of each block. This is dimension of block in number of threads. Each such parameter has a type dim3. This is the type of our variables, which is an integer vector type of three elements: x, y, and z. X, y, and z. These three elements specify the size of the three dimensions. The programmer can use fewer than three dimensions by setting the size of the unused dimensions to 1. So we have three dimensions in grid, three dimensions in block, but we can specify to 1 if we don't need to, like if our array is one dimension, then why we are using x and y, or why we are using y and z. For example, the following host code can be used to call the vec at kernel function and generate a 1D grid that consists of 32 blocks, each of which consists of 128 threads. The total number of threads in the grid is 128 multiplied by 32 equals to 4096. Okay, let's understand this. So we have blocks, right? But we have 32 grids. No, sorry. So in grid we have 32 blocks. So we are specifying the block number in here. And then each block has 128 threads. And also, based on the latest progress in CUDA and GPU development, we can specify until 1024 threads because of the limitations. Okay, note that dimension block and dimension grid are host code variables that are defined by the programmer. These variables can have any legal C variable name as long as they have the type dim3. So you can change these names to dog and cat. For example, the following statements accomplish the same results as the statements above. Okay. The grid and block dimensions can also be calculated from other variables as I said earlier. So this is sale function n divided by 256, and then we are calculating this one, and then there is each block has 256 threads, and then each grid has this calculation and one on one. Okay, this allows number of blocks to vary with the size of the vector so that the grid will have enough threads to cover all vector elements. In this example, the programmer chose to fix the block size at 256. The value of variable n at kernel call time will determine dimension of the grid. So this is important. The value of variable n at kernel call time will determine dimension of the grid. So since our grid dimension has dependency to n, so we need to calculate n, right? And when it's happening, it's at kernel call time. So it's not like earlier. If n is equal to 1000, the grid will consist of 4 blocks. If n is equal to 4000, the grid will have 16 blocks. In each case, there will be enough threads to cover all the vector elements. Once the grid has been launched, the grid and block dimensions will remain the same until the entire grid has finished execution. Okay, so grid is launching, and then until all of the execution, all of the parallel computation happening, and then it's gone. It's gonna be deleted, of course. For convenience, CUDA provides a special shortcut for calling a kernel with one-dimensional grids and blocks. Instead of using dim3 variables, one can use arithmetic expressions to specify the configuration of 1D grids and blocks. In this case, the CUDA compiler simply takes the arithmetic expression as the x dimensions and assumes that y and z dimensions are 1. This gives us the kernel call statement shown in figure 2.12. Where is 2.12? Anyway. So instead of using dim3 variables, okay. So normally we are using these dim3, okay, to specify these. And then it says we don't need, if we don't want to, we can just put these x and y, not x and y, we can put these in here and this one in here. And so normally in our system, in dimension 3 variable, we are using 1 and 1, 1 and 1 every time, right? So you can change all of these y and z dimensions, but it says we don't need to put those dimensions as the x dimensions, and assumes that the y and z dimensions are 1. So it assumes from the arithmetic expression. Readers who are familiar with C++ would realize that this shorthand convention for 1D configuration takes advantage of how C++ constructors and default parameters work. The default values of the parameters to the dim3 constructor are 1. Okay, so it's because of this constructor stuff on C++. That's why it just, like, as always, it just put 1 automatically. When a single value is passed where dim3 is expected, that value will be passed to the first parameter of the constructor, while the second and third parameters take the default value of 1. The result is a 1D grid or block in which the size of the x dimension is the value passed, and the sizes of y and z dimensions are 1. Within the kernel function, the x fields of variables greatDim and blockDim are pre-initialized according to the values of the execution configuration parameters. For example, if n is equal to 4000, references to greatDim x and blockDim x in the vect at kernel. So in our kernel, of course, will result in 60, 16, and 256 respectively. Note that unlike the dim3 variables in the host code, the names of these variables within the kernel functions are part of the CUDA-C specification and cannot be changed. That is, the greatDim and blockDim are built-in variables in a kernel and always reflect the dimensions of the grid and the blocks respectively. So these are built-in variables, always reflected. Okay, it's always the size of the you're just specifying the dimension and you cannot change these. Okay, in CUDA-C the allowed values of grid x range from 1 to 2 to the power of 31 minus 1, and those of grid y and z range from 1 to 2 power to the 16 minus 1. All threads in a block share the same block ID x, block ID y, block ID z values. Yes, because so think about this. Think about okay. Yeah, this one. So think about this. What the fuck is this? Think about this. So we have block, right? And this block has 3 dimensions: x, y, and z. I'm always bad at drawing. X, y, and z. Okay, these are the dimension of block, and this block in the each block are inside a grid. Okay, grid, and then this block has threads, a lot of threads, like 10,000, 10 million maybe. Each has threads, and each these threads are belongs to block, and all of these threads are the same in the same block dimension, has the same block dimension. Okay, sorry. Let's get back. Nope, I don't want it. Nope. Huh. Okay. So we now turn our attention to the configuration of blocks. Each block is organized into a 3D array of threads. Two-dimensional blocks can be created by setting z to 1. One-dimensional block can be created by setting both y and z to 1, as in the vector at kernel example. As we mentioned before, all blocks in a grid have the same dimensions and sizes. The number of threads in each dimension of a block is specified by the second execution configuration parameter at the kernel call. Within the kernel, this configuration parameter can be accessed as the x, y, and z fields of block dimension. The total size of a block in current CUDA system is limited to 1024 threads. These threads can be distributed across the 3 dimensions in any way as long as the total number of threads doesn't exceed 1024, for example, block dimension. So you can specify any threads number inside of a block dimension, but it cannot exceed 1024 because of the limitation. Yeah, this is the figure for grid and all block and threads, of course. So you can choose the block dimension to 5, 12, 1, 1, 8, 16, 4. You should multiply these variables, and then 32 to 16 are all allowed, but 32 to 32 to 2 is not allowed because the total number of threads would exceed 1024. A grid and its blocks do not need to have the same dimensionality. A grid can have higher dimensionality than its blocks, and vice versa. For example, it's a show a small toy grid example, yada yada yada. So it doesn't. Sorry, it's 830 in here. So it's not dependent to each other, the block and grid sizes. The grid consists of 4 blocks. In this example, it talks about blocks organized into 2 to 2 array. Each block is labeled with block index y and x. For example, block 1 0 has block index y1, block index x is 0, because you know. So in here, okay, get back to drawing. So in here, oh, for example, okay, for example, 1 0 0, okay, 1 0 0. So it's not starting from x to y and z. It's from starting from z, y, and x. In, for example, block 1 0 has block y 1, block x 0. Yeah, I talk about this one. And if there is no z, it's starting from y and x. So it's always starting from y. Not always, of course. If there is z, that starts from z. Okay. So yeah, we are in here. Note that the ordering of the block and thread labels is such that highest dimension comes first. Okay, let's highlight this one. And also I'm gonna check something. This notation uses an ordering that is the reverse of that used in the C statements for setting configuration parameters, in which the lowest dimension comes first. This reversed order okay, nothing happening. I'm just gonna check the live stream. Okay, nothing wrong. Let's quit from Safari. So yes, this reverse ordering for labeling blocks works better when we illustrate the mapping of thread coordinates into data indexes in accessing multidimensional data. Each thread index also consists of 3 fields: the x coordinate, the y coordinate, and the z coordinate. This figure probably this figure, not this one, the other one, the previous one, illustrates the organization of threads within a block. In this example, each block is organized into 4 2 arrays of threads. Since all blocks within a grid have the same dimensions, we show only one of them. Fig 3.1 expands block to show its 16 threads. For example, thread 1 to 102 has tracking index z1, y0, and x is equals to 2. Note that in this example we have 4 blocks of 16 threads each, with a grand total of 64 threads in the grid. Okay, we use these small numbers to keep the illustrations simple. Typical CUDA grids contain thousands to millions of threads. Yep. And also this is a figuration. This is a figure for 2-dimension grid, and each grid has blocks, and each blocks has a lot of threads. Mapping threads to multidimensional data. Okay. Okay, the image below left, and then there is matrix multiplication and summary. Okay. So I gotta be fast. Almost 20 minutes left for the meeting, and also I think I can go 50 minutes later, and 35 minutes we have left. The choice of 1D, 2D, 3D thread organization is usually based on the nature of the data. For example, pictures are a 2D array of pixels. Using a 2D grid that consists of 2D blocks is often convenient for processing the pixels in a picture. Figure shows such an arrangement for processing a 62 to 761 f1f picture. So 62 pixels in the vertical or y direction, and 76 pixels in the horizontal or x direction. Assume that we decided to use a 16 to 16 block with 16 threads in the x direction and 16 threads in the y direction. We will need 4 blocks in the y direction and 5 blocks in the x direction, which results in 4 to 5 equal to 20 blocks, as shown in figure 3.2. The heavy lines mark the block boundaries. The shaded area depicts the threads that cover pixels. Each thread is assigned to process a pixel whose y and x coordinates are derived from its block index, block dimension, and thread index variable values. And vertical row coordinate is block index y multiplied by block dimension y plus thread index y. And also it's the same for the horizontal, but changing is the dimension. For example, the pin element to be processed by thread 00 of block 10 can be identified as follows. Yep. So pin element is dependent to all these variables. Okay, so it depends on threads y coordination, block index y, multiplied by block dimension y, and then there is block index x multiplied by block dimension x, and also thread index s x. Okay, note that in figure we have 2 extra threads in the y direction and 4 extra threads in the x direction. So what's gonna be happen to those extra threads? So we're gonna put some kind of variable to not run, to not execute those threads, because we don't need those ones. Okay, that is will generate threads to process. This is similar to the situation in which 1000 element vector is processed by the 1D kernel at kernel. Okay, this was from chapter 2, using 256 thread blocks. We call that an if statement. So we need if statement in here. And based on that if statement, we are gonna choose to execute or not these threads. Is needed to prevent the extra. So yeah, we are preventing the extra 24 threads from taking effect. Otherwise, it's gonna be it's not gonna be optimizing. Similarly, we should expect that the picture processing kernel function will have if statements to test whether the thread's vertical and horizontal indices fall within the valid range of pixels. Yes. We assume that the host code uses an integer variable n to track the number of pixels in the y direction and another integer variable m to track the number of pixels in the x direction. We further assume that the input picture data has been copied to the device global memory and can be accessed through a pointer variable pin d picture in device. The output picture has been allocated in the device memory and can be accessed through a pointer variable picture out device. The following host code can be used to to the kernel color to grayscale conversion to process the picture as follows. So okay, we have our dimensions in here, and these are from device. So these m and n is for using these if statements, and this picture in d picture of d is for our input, for to take input picture in to the device. The dimensions of the grid, on the other hand, depend on the dimensions of the picture. Okay, so you can specify. So it says just like we just fixed the dimension of block, and the grid dimension is dependent to m and n. That's why. So yeah, the grid dimension is dependent to those variables. So it says to process the picture view generate 10 11 750 blocks, 94 in the y direction and 125 in the x direction. Within the kernel function refers to dimension x, dimension y, dimension block dimension x, and block dimension y will result in 125, 94, 16, and 16 respectively, of course. Before we show the kernel code, we first need to understand how C statements access elements of dynamically allocated multidimensional arrays. Ideally, we would like to access pin picture in device as a 2D array in which an element at row J and column E can be accessed as pin D, G, I. Element accessing. However, the ANSI standard on the basis of which CUDA-C was developed requires the number of columns in pin to be known at compile time for pin to be accessed as a 2D array. Unfortunately, this information is not known at compile time for dynamically allocated arrays. In fact, part of the reason why one uses dynamic allocated arrays is to allow the sizes and dimensions of these arrays to vary according to the data size at runtime. So this is important part of the reason why. Okay. So why it's useful, because we are finding out the data size at runtime. Thus, the information on the number of columns in a dynamically allocated 2D array is not known at compile time by design. As a result, programmers need to explicitly linearize or flatten a dynamically allocated 2D array into equivalent 1D array in the current CUDA-C. Okay. In reality, all multidimensional arrays in C are linearized. Okay. This is due to the use of a flat memory space in modern computers. See the memory space sidebar. Where is the memory state sidebar? Yeah, it's in here. So we are flattening all these dimensions for because we are using flat memory space in our memories, and that's why we are linearizing or flattening it, the 2D array, into equivalent of 1D array. Okay, in the case of statically allocated arrays, the compilers allow the programmers to use higher dimensional indexing syntax, such as x and y, to access their elements. So it's making our job easier. That's why we are using these multidimensional grid or multidimensional uh, blocks. Under the hood, the compiler linearizes them into an equivalent 1D array and translates the multidimensional indexing syntax into a 1D offset. Okay. So also the program itself is translating our indexing syntax into a 1D offset. This is important. In the case of dynamically allocated arrays, the current CUDA-C compiler leaves the work of such translation to the programmers owing to lack of dimensional information at compile time. Okay. A memory space is a simplified view of how a processor accesses its memory in modern computers. A memory space is usually associated with each running application, the data to be processed by an application, and instructions executed for the application are stored in locations in its memory space. Okay, these memory spaces are associated with each running application. Okay, and all of the data, all of the space is going, all of them are gone after the process happened. Like all of the grid execution finished, and then all of them is freed. Each location typically can accommodate a byte and has an address. Variables that require multiple bytes, 4 bytes for float and 8 bytes for double, are stored in consecutive byte locations. When accessing a data value from the memory space, the processor gives the starting address of starting byte location and the number of bytes needed. So we are gonna calculate how many bytes we need, where is the starting point the of the array or index. Okay, most modern computers have at least 4G byte-sized locations where each G is yada yada yada. All locations are labeled with an address that range from 0 to the largest number used. Since there is only one address for every location, we say that memory space has a flat organization. As a result, all multidimensional arrays are ultimately flattened into equivalent one-dimensional arrays. While a C programmer can use multidimensional array syntax to access an element of the multidimensional array, the compiler translates these accesses into a base pointer that points to the beginning of an element of the array, along with a one-dimensional offset calculated from these multidimensional indices. Cool. So how many page left before image blur? And then there is image blur, there is matrix multiplication, and then done. 68. Okay. 68. We just need 14 pages. Okay, we are in here. There are at least two ways in which a 2D array can be linearized. One is to place all elements of the same row into consecutive locations. The rows are then placed one after another into the memory space. This arrangement called the row major layout is illustrated in here. To improve readability, we use M, J, and I to denote an element of M at the jth row and the eth column. MGI is equivalent to C expression, but slightly more readable. Figure shows an example in which a 44 matrix M is linearized into a 16 elements of 1D array with all elements of row 0 first, followed by the 4 elements of row 1, and so on. Therefore, the 1D equivalent index for an element of M at row J and column I is J multiplied by 4 plus I. The J multiplied 4 term skips over all elements of the rows before row J. The I term then selects the right element within the section for row J. For example, the 1D index for M to 1 is 2 multiplied by 4 is equals 8 plus 1 equal to 9. This is illustrated in which is in which M9 is the one equal of. This is the way in which C compilers linearize 2D arrays into 1D array, flatten it, linearizing it. Another way to linearize is place all elements of the same column in consecutive locations. The columns are then placed one after another into the memory space. This arrangement called the column major layout is used by Fortran compilers. Note that the column major layout of a 2D array is equivalent to the row major layout of its transposed form. We will not spend more time on this except to mention that readers whose primary yes primary previous programming experience with Fortran should be aware that CUDA C uses the row major layout rather than a column major layout. Also, many C libraries that are that are designed to be used by Fortran programs use a column major layout to match the Fortran compiler layout. Okay, in C, some of the libraries are using column major layout. As a result, the manual pages for these libraries usually tell the users to transpose the input arrays if they call these libraries from C programs. We are now ready to study the source code of color to grayscale conversion. Shown in figure, the kernel code uses the following equation to convert each color pixel to its grayscale counterpart. So this is how row major layout for a 2D C array. The result is an equivalent 1D array. It turns okay. So it takes this row, putting in here, and then from this point, it's just like, okay, what is it doing? So it goes until end of the row, okay? And after end of the row, it just points out to this another row start point. And so if you know how pointers are working, you can it's so easy to understand what is going on here. It just this normally points out to nowhere. It just points out to here, and then this one is just points out to here, and this one is just points out to here, and all it starts from M. Okay, let's go. So this is source code of color to grayscale, conversion width to the thread mapping to data. So as far as I know, it's a CUDA code, CUDA C code. This is function color grayscale conversion, and it takes okay. There are variables in here. Okay, and there's p out. You are giving the picture out variable, picture in variable. Picture out will be just, how can I say, it can be empty, and then there's width and height. And so in this called row, it's just like taking column from block id x plus thread index x, and taking row from y multiplied by block dimension to block index plus thread index y. So okay, and then get 1D offset for the grayscale image. Row multiplied by width plus column. Okay, one can think of the RGB image having channel times more columns than the grayscale image. RGB offset, graph offset per channels, all the channels, and it just takes breadth value, and then based on this RGB offset, you are just taking green and blue value, and then we are doing our function or equation to grayscale, and then we multiply by floating point constants. Yeah, these are the constants in our equation, etc. Okay, so we were here. So this is our grayscale conversion equation. There are a total of block dimension x, grid dimension x threads in the horizontal direction. Okay. Similar to vector addition kernel example, the following expression generates every integer value from 0 to block dimension x multiplied by grid dimension x minus 1. This one is doing that. And then we know that grid dimension is greater than equal to width enveloped in the host code. We have at least as many threads as the number of pixels in the horizontal direction. We also know that there are at least as many threads as the number of pixels in the vertical direction. Therefore, as long as we test and make sure that only the threads with both row and column values are within range, that is, column smaller than width and row is smaller than height, we will be able to cover every pixel in the picture, and we are not exceeding our width and height. We can generate a 1D index for the pixel at the row and column call at row width call plus call. This is 1D index. Gray offset is the pixel index for picture out. Since each pixel in the output grayscale image is 1 byte, using our 62 to 76 image example, to derive 1D index of the P out pixel calculated by the thread 00 of block 10 with the following formula. So this notation is calculating our pixel number. As for p in, we need to multiply the gray pixel index by this one, since each color pixel is stored as 3 elements, each of which is 1 byte. Every one of them is 1 byte. The resulting RGB offset gives the starting location of the color pixel in the pin array. Yeah, okay. The resulting RGB offset gives the starting location of the color pixel in the pin array. We read the RGB value from the 3 consecutive byte locations of the pin array. Perform the calculation of the grayscale pixel value and write that value into the p out array using gray offset. In our image example, the linearized one, the index of the first component of the p in pixel that is processed by thread block can be calculated with the following formula. Okay. The data that is being accessed, I think we are gonna understand what is going on with this stuff. I'm still not understanding it. Okay, is the 3 bytes starting at byte offset illustrates the execution of impersonating our example, assuming blocks calling the color to grayscale conversion kernel generates threads, number of threads. The grid will have 20 blocks, 4 in the vertical direction and 5 in the horizontal direction. The execution behavior of blocks will fall into one of 4 different cases shown as 4 shaded areas in figure 3.5. Where is 3.5? Is that 3.5? No, these are not 3.5. The first array marked 1 consists of the threads that belongs, yeah. So this is the first, second, third, fourth. These are like all 16 blocks. The second area marked 2 in conditional test. Mm-hmm. 16 needs to cover 76 pixels, 80. As a result, 12 threads in each row will find their call values within range and will process pixels. The remaining 4 threads in each row will find their column values out of range and thus will fail the if statement condition. These threads will not process any pixels. Okay, overall of the threads in each of them. The third array mark 3 in accounts for the 4 lower left blocks covering the medium shaded area of the picture. Although the column values of these threads are always within range, the row values of some of them exceeds the n value. This is because the number of threads in the vertical direction is always a multiple of the block dimension y value chosen by the programmer. The smallest multiple of 16 to cover 62 is 64. As a result, column will find the range and will process pixels. We need to address in each column will not pass and will not process any pixels. Overall, 224 of the 256 threads will process pixels. The fourth area marked for conditional threads that cover the lower right, lightly shaded area of the picture, like area 2, 4 threads in each the top 14 rows will find their column values out of range, like area 3, third area. The entire bottom 2 row of this block will find their row values out of range. Overall, only 168 of 256 threads will process pixels. We can easily extend our discussion of 2D arrays to 3D arrays by including another dimension within an array. This is done by placing each plane of the array one after another into the address space. Assume that the programmer uses variables m and n to track the number of columns and rows respectively in a 3D array. Okay, we were using m and n to track the number of columns and rows. So now we need another one to track which plane are we in. When calling a kernel in the kernel, the array index will involve another global index. The linearized access to 3D array P will be in the form of P plane m to n plus row m plus column. Okay. A kernel processing the 3D P array needs to check whether all the three global indices plane row call fall within the valid range of the array. The use of 3D arrays in CUDA kernels will be further studies for the stencil pattern in chapter 8 stencil. Okay. So chapter 3.3 image blur, a more complex kernel. Okay. I think I should be stopped in here. Okay, I'm gonna write I stopped in here. Where is the text? Yes. Where is the text? Can I write? What is this one? Text selection. No. Yeah. I want to write. I'm gonna say stopped live in 3.3. Okay. So probably I'm not continue today, but maybe tomorrow. I think tomorrow I'm gonna be all live. Yeah. Probably some kind of live coding and also live reading a book. Maybe after finishing chapter 3rd, I'm gonna continue with chapter 4th. And then what else? Yeah, also I need to show. Yeah, I need to show my new blog post on Substack. So it's called llmengineer.substack.com. I just wrote down this blog post just yesterday. It's all about mixture of experts. I think I liked this style of micro essay, and as you can see, it's not like 1,000 or 10,000 words of blog post. It's just maybe 500 or smaller than 500, just like 2 or 3 minutes to read, It's a little bit hard to understand in these micro essays, but I'm just trying to the giving the, how can I say, insights. And then if you liked it, if you like the mixture of experts, you can definitely go to these blog posts. One of them from Hugging Face, one of them from Google, one of them from Mistral, and also shout out to my friend Juan. And you can read these articles to learn more about it. And yeah, that's it from today. I'm just gonna leave in here. So have a good one. Bye bye.